Okay, good morning. So my name is Maciej Hoffman. Last week, Tomasz Svoboda kindly jumped in and he did the lecture on search 1, which was what we call uninformed search, because you have no extra information. You basically have to search through the state space without knowing anything else. And today we will look also at informed search, which is you have some extra information, some heuristics, you have some idea how far the goal may be, but we will see the details later. So I assume that the connection is okay and that everything is clear. If not, stop me or write into the chat. Okay. So let's get started. So there are two variants of the search. One is tree search, which means that, well, so what is the difference between tree and a graph? So tree doesn't have cycles, right? And so you have two kinds of state spaces. One that is a tree, and one that is a general graph that may have loops, that may have cycles. And the search algorithms that we're studying are applicable to both state spaces. But there are two variants of these search algorithms. One is called, tree search, and one is called graph search. So it's a bit confusing. We will see the details later, because you can actually apply a tree search variant also to a general graph, but it may not be the best thing to do. So we will see what the exact differences are. But so far you have seen the tree search variant of all these search algorithms, which is the easier one, because you don't, we will see the details in a little bit. But the main part of today's lecture will be about the heuristics and eventually the famous A* search, which is something that you will also have to implement during the assignments. It's the first big assignment in your labs. So I will run some demos now, and so I'll share the screen, and let's see if everything works out. So, okay, let's make a poll if everything is okay. So do you see my shared screen now and everything works for you? Nice. Good. Okay, so you have this maze. So it's actually just a grid, and here is the start, and here is the goal that you need to reach. So every edge basically costs 1. Okay, so it's a graph that doesn't have any specific costs, and what we will see now is a run of the breadth first search algorithm on this state space. And so let's see if I can make this bigger, maybe. Maybe that's gonna be better. So I have just started it. So this is the state space. It's a similar kind of code that you will be dealing with during your assignments. And maybe I can stop sharing also my camera just to spare some bandwidth. Okay. Right. And you're starting here and you're running the breadth first search. And here is basically what the algorithm is doing. So it's expanding from the start. It's 4.0 means because we're doing this, we're calling the, so in this case, it's written first the column and no, sorry, yes, and second the row, which may not be actually the convention during the lectures, but in this case, it's written like this: 4.0 at depth 0. That's the start, and you're expanding that, right? And you're adding 4.1, which are these pale green, and 3, 0 at depth 1. Okay, depth 1 because it costs 1 to get there. So far so good. So we do the next step. And this here you see the frontier. And so we're running breadth first search. That means, we first have to expand everything that is at a given depth. Only then we can move to nodes that have a bigger depth. Okay. This. So just run a couple of iterations, and so you see that it was sort of expanding the frontier in the state space, but you see that it's somehow progressing very slowly, and the frontier is getting big. And so what is going on? Why do we have so many? Why do we have so many nodes in the frontier? So this is the frontier, and so this is the search tree, right? And so I guess you already touched upon it last time. There are two things. There is the state space, the number of states it's given. In this case, it's 4 by 4, and they have unique identifiers. This is state 4, 0. This is state 3, 0. This is state 2, 0, etc. And then you have these nodes in the search tree, which are things that you already explored. In this case, it's the frontier. And so the problem here is that you see multiple instances of the same node. So here you see 4, 1 and at depth 3. Here you see again 4, 1 at depth 3 and again. And the reason why you have this is because you're running tree search, but your state space is not a tree. It's actually a graph. So the thing is that you have several. So in this case, we said 4, 1. Which is actually the starting which is this node here. You have several ways of arriving there, such that it's at depth 3. So for example, I can go 1, 2, 3, okay, or I can go 1, 2, 3, or I can go 1, 2, 3, and all these just make it to the frontier because we're not doing any additional checks. We're just blindly running tree search. And because there are these, everything is connected with everything using undirected edges, we have these multiple instances of the same node on the frontier. Okay, and this situation is going to get even worse as we move on, because there are going to be even more and more ways of getting to a particular node with the same number of steps. So this will be at the same depth. And remember that we're running breadth first search. So for example, we have some nodes that are at depth 3. All of these need to be expanded first. And only once we are done with all of them, we can actually move to depth 4. Okay. So this is what is happening here. So it's somehow progressing slowly, and you see that there's a lot of, it's wasting a lot of resources. So this illustrates basically the tree search on something that is actually not a tree, but a graph, and this is a sort of fully connected graph, or at least there's a lot of redundancy how you can go get from one node to another. Yeah, so I might just run it till the end, and you see there's a lot of things going on, and so the goal is at depth 8, and so you see that this is highly inefficient. Actually, it would be, in this case, because it's a breadth first search, it would be fine to stop as soon as you reach the goal, which has already happened. But this is a general sort of algorithm that works also for the uniform cost search that you have already seen last time. And there you may remember that you first need to you can only finish once you expand the goal, not once you reach it, because you may in the meantime find other routes to the goal that are shorter. So this is what is happening now. So I might just stop it, I think that, yeah, it already stopped. So you've seen that it has done a lot of work to get there. So such that I don't have to switch back and forth with my screen. So let's change here tree search to false and run this again. And you see that now it's completely different, right? The frontier doesn't have many nodes, and it's running the graph search algorithm now, which you will see in a second, which does one important additional step, which is checking which states, so which nodes in the state space have been already visited, and it's not adding them again. And that saves a lot of resources, right? Because only one state can be only expanded only once and can be also on the frontier only once, even though there might be different ways to get there. But the shortest one will be will be part of the search. If you find a shorter one, then it gets updated. But yeah, it doesn't lead to the inefficiency that you have seen before. Okay, so it proceeds like this, which is something somehow you would expect, and there you are. And this is the shortest path. In this case, it's one of the shortest paths, because there would be multiple solutions of the same length. Okay, any questions to the demo? Okay, let's continue then. So stop sharing the screen. We're back on the slides. So let's look at the algorithm. So this is the tree search, which is the simpler variant. But in case your state space is not a tree, it actually leads to this inefficiency that you have just seen. So here's the pseudocode. So you initialize the frontier, and then while there is something on the frontier, you pop. That means you take what is at the top at the beginning. You check if it's the goal, and if not, you expand the. So note that the node is something in your search tree, whereas the node state are the coordinates in the state space. Okay, that's something to keep in mind all the time here. Yeah, as you expand, that means you look through the neighbors and you add those nodes to the frontier. And yeah, that's basically very, very simple. And but it's missing one important part, which we will see here, and that's the graph search. So graph search is because it's suited for graphs, which are general graphs where you can have everything connected to everything, right? Unlike trees that don't have cycles. So it's the same thing, but there is this additional data structure called explored set, and you initialize it to be empty, and here you add so as you pop something from the frontier, you add the node state, so the state to the explored. So that's something in the state space, and that should be explored only once. Otherwise, it's the same thing. And here is this additional condition. If node state is not in explored or in frontier, then add to frontier. Okay, so something that has been explored or that already is on the frontier, you just don't add it. And that's it. And again, do not forget, node is not the same as state. Okay, that's also important when you're programming, because this makes a difference that you have to add this. You actually have to add the state such that this doesn't get repeated. So that's that. For the data structure you can use for the explored set, what would you use? Stack. Okay, other ideas? Why would you use a stack? Queue. Okay. Just the list might be fine. Okay, so this is getting, I think this is an interesting discussion. So I'm not asking for the frontier, right? So you may already have had the discussion about how to implement the frontier, and there, let's see if more ideas come up. So for the explored set, so there's no, because the first to enter should be the first to go. Well, not quite. So I think you're confusing the frontier with the explored set. So for the frontier, for the frontier, so yes, okay. So we had two basic algorithms: the depth first search and the breadth first search. So for, you mean different? So for, but let's clarify this. I think it's important. So for let's say for the depth first search, so DFS, and you need to implement the frontier. What would you use for the frontier with DFS? Well, let's make a poll. Stack. Yeah. Well, okay. Let's. Yeah. It's the stack indeed, because you're always kind of, you're going deeper and deeper into the tree, and the new nodes that you discover will be expanded first. That's why it's going into the depth, because whenever it encounters a new node, it dives deeper and deeper. So those that are sort of at the that you have discovered recently will be expanded first. Indeed, yeah. And for the breadth first search, for the frontier, for BFS, what do you use? You use the queue, right? Because it's first come, first serve. So those first that come first on one level should be explored first. So in that case, they come first because they are the shallowest, and they should be done first. That's why it's going, that's why it's breadth first search. Perfect. Yeah, so that's fine. But now I was asking something different, which is I need an additional data structure just to keep track of which nodes in the state space I have already visited, right? And I could just use a list because I don't, but it's still not the optimal one for this. So it has this, I don't care basically about the ordering. I just need to know whether it's there. And I have this, indeed, it's the set, right? Because it has this additional property that every state should be there just once, right? And that's an important property. That's why, it leads to this more efficient variant of the algorithm. So the states are unique, there's in the state space, there's only every state is there only once. So that means, a set is a logical choice here, right? Because we don't want to repeat the states. So in a list, if we had multiple instances, then we would, we would just make it less efficient, because we would have to be, we would basically just at least memory efficient, because we would basically have to add them multiple times, and also then even the looking up whether at least one is there would take longer. So set would be great for the explored set, which is intuitive. Good. I think this was a very useful discussion that helps you to understand what is behind. Okay. Right. So the breadth first search, graph search. This is just to make you aware of this additional condition, so or that you have this explored set that you have to take into account. So basically you just need this additional data structure, and you just need to put the right check at the right place, and that's it. Here you see, because it's breadth first search, the frontier is a queue and the explored set is a set. Okay, I think that's other than that, there's nothing really complicated here. So the main idea, do not expand the state twice, and that's it. Okay. And the demo we have already run. So if we can move on, and we can move to the uniform cost search, which is something that you started already last time. And so the difference here is that the edges in the state space, they have actual costs, right? It's not that if you move from A to B, it's always 1, but let's say here from B to C, it costs only 0.5. Okay, so that makes it a bit more general, and of course also more applicable. It's like when you have this scenario with the roads that have some distances, for example. And for this, we have this uniform cost search. Before you had the tree search variant. Now we can also do the graph search variant. And so let's see how this will look like. So we will see the algorithm in a second, but to give you the idea, let's look at the run on this particular space. So I'm in S, which is the start, and my current cost is 0. And I'm expanding it, and I'm getting A with a cost of 1, C with a cost of 1.2, and D with a cost of 3. So question for you is which node will be expanded next. So for this, I think I can use a poll. Just hold on, don't write anything. Start a poll, A, B, C, D. There's no B, but that doesn't matter. Which one do I expand? Okay, so let's publish. Okay, everybody picked A, which is correct. So unlike in the breadth first search, these would be all on the same depth, so at the same level, but here the actual costs matter. So I will choose the smallest cost, which in this case is 1. So I will expand A. Okay, nice. And this gives me this. Okay, so next I get B 2 and E 2.5. Okay, so now it's easy. So the next to be expanded, I just take the minimum from what I have, this is expanded, so this is removed from the frontier. So the frontier are these pale gray ones, and the next to go will be C. And I'm getting this. Okay, and now there's one thing to note, and that is that I have 2 times B here. Okay, so I have arrived to B from, like, so I can go through A, which gives me a total cost of 2, but I can also go through C, which gives me a total cost of 1.7. So what do you think I should do now if I want to have something like we saw before, something like a graph search variant of things? So from A, you also decide the cost of C. Okay, there is, let me see, there's a question. So from A, you also decide. So you mean the cost of C is here. This is a direct link from S to C, which costs 1.2, or what was your question, Elisa? So we're not only in one place at a time. So we're building the search tree, and this is the currently where we are. This is what we explore. This is on the frontier, and we have all that information. We're not only in one place. We just choose one place where we expand the frontier, and the cost is the shortest path up to every node in the state space. So I'm not sure I'm getting your question right. You can also use your microphone if you like. It's up to you. Okay, never mind. I think you have to do it when you log into the session. Exactly. Or you can also draw if you want. Why would it matter the smallest cost to A if you're going to analyze the rest too? Well, the point is that the smallest cost to every node matters, because you want to find the shortest path. That's why the algorithms, some of the algorithms, including this one, are optimal. So it does matter, and that's actually the point, that for every node in the state space, I want to know the shortest path, and then I have the right information which one I should expand. So okay, yeah. So we can, let's continue, and hopefully it will become clear as we go. What about D then? Well, so look, so this is the frontier, and so initially we didn't have any information. We just expanded the start, right? We got these 3, and we have the costs. So in the breadth first search, this was, how many steps we did, but in this case, it's the actual cost of the edges. So it costs 1 here, it costs 1.2 here, and it costs 3 here, and 3 is actually a lot. So D is here on the frontier, but it will probably remain on the frontier for quite some time because 3 is a big number, right? So it is on the frontier, but it's basically going to be last. So in this case, it's not a simple queue like before. It's going to be a priority queue, weighted basically by the cost so far. So this is currently going to be at the end of the queue, and only once this will become the smallest number will we expand the D. Okay, so in that sense, it's on the frontier, so we're checking it, but it's going to have to wait because it was expensive to get there. So in the way how this algorithm works, it will, choose other options first that are cheaper. Yes. This is why we check C node after A. Yeah. Yes, exactly. That is exactly the point, right? Because here we had 1, but here we have 2 and 2.5, but that's, bigger than 1.2. So this came next. Exactly. Okay, but now what I wanted to talk about, which is a little tricky, is that we have these 2 times B, and you see this graph search here, which means, just like we saw before, we don't want a node from the state space 2 times here, right? Because it's actually, there's only one node B in the state space. So what we want to keep only the one that is cheapest, right? Because we don't want to get into this redundancy thing, which is make our search inefficient. So what we're going to do now is we're just going to cross out this one because it's bigger than 1.7. So we're not interested in this anymore. We're not interested in getting to B through A because we have a cheaper path. So we just go to this, okay? And it's going to disappear. And at the same time, there was another thing that disappeared, which was this D3, because we have a D2.2. So we don't need this D3. We are happy with D2.2. Exactly. Good. Okay, so let's make another poll. So what are we going to expand next? We don't have all the letters we need, but it's okay. The right answer is among the ones I asked. Okay, perfect. Indeed, yes. So we just look for the smallest number around, which is 1.7. So you're going to expand B. And you get this. So here again, you check the sort of duplicity of these states. You see EE, FF, which is not good. So, and these were actually, more expensive, 2.7, 3.7. We don't need those anymore. So this didn't help us, but we couldn't know. So that's what. And here we go from D. So because now 2.2 was the smallest on the frontier, and we get to the goal. Hooray. Can we stop here? Are we done? So let's make a poll. Who thinks we can stop here? Say yes. Okay, so most of you say no. Elisa has also a question, but so let's see if that becomes clear. So yeah, so the correct answer is no, and so that's the sort of tricky part about the uniform cost search, is that it is possible that you can still find an alternative route to the goal, which is cheaper. This cannot happen in the breadth first search, because basically you go level by level, and you can find something that is at the same depth. So an alternative route that would be the same, of the same cost, but that is not interesting. But in this case, it's not like that. And so you can only stop once you're expanding the goal, which makes sense, because you are now at the goal with 3.2, but you still have these things here like 2.5, 2.4, 1.7, and if some of them can make it to the goal cheaper than 3.2, which is well possible, then you shouldn't discard them. So only once this goal with a number becomes on the frontier the cheapest, only then you can be sure that you can stop. So what you have to do now is you have to expand. You have to expand here. So this 1.7 is not on the frontier anymore, okay? Because it's we already expanded it, okay? So frontier was just this. We take this 2.4. We have 2.9. Okay, so we're doing better. But still, we cannot stop because we still have 2.5. Maybe we can get to the goal even cheaper. So we cannot stop. Okay, we have 3.5. These are all now dark gray. So this is the frontier, and something with the goal is now cheapest on the frontier, which finally means we can stop, and we have the guarantee that we have found the optimal path to the goal. So is this somehow clear also for you, Elisa? Or does it? I think it's the same for the goal like for any other node, that the algorithm basically takes into account the possibility that you can find cheaper routes to some nodes. Isn't the algorithm going to check D3 after we know it is the well, there's no need to check D3 because we had this D2.2, and we cannot possibly win anything by doing anything from D3, because we already have D2.2, and it's the same D in the state space. We just have a cheaper path, so it's not interesting to sort of take into account longer paths to the same state. So we have D here, 1.2 plus 1 or 3, and we need to get to the goal with the cheapest route. So it's not interesting to keep alternatives that were more expensive. So this is not useful at all because we have this thing here. So we just don't need that, and it's that we're never ever gonna need that. The point is that if it's the same letter, so if it's the same node in the state space, we're only interested in having it once and with the cheapest costs. With the cheapest cost. Right. So is everything clear now? Okay. Good. Very good. Okay, so let's look at this is written. kind of, the same thing here. Here it's a priority queue. It's ordered the frontier by the costs so far. Here is the explored set. So there's nothing really difficult about this. And here is the step that was not in the depth first search, but that is needed here, which is what we just discussed, which is that if something is there with a higher cost, then you should replace it with something that you have found that is of lower cost. And you're gonna have that state there only once with the currently cheapest cost. Okay. Yeah, I think we have also run the demos. I think for you to get the idea, it's fine. So to get an overview, so we had these sort of three basic algorithms here, and the main difference between them is what they pick from the frontier, how they choose, what they expand next. So if we look at it in this way, so it's some kind of argmin, so that means of some function f, so that's some kind of evaluation of the nodes on the frontier. Okay, and what would be that function for DFS or BFS or UCS? Probably the easiest for you to start with would be this breadth first search. So what would be, do you have any idea what FN would be? So it's a node evaluation, and you will be taking the minimum to expand. So how the nodes are evaluated in the breadth first search. Any ideas? With fewest children. That's an interesting thought, but I don't think that any of the algorithms works like that. It would probably not be complete. It would not be. That's an interesting thought. I mean, it may have some advantages in particular problems, but it may not be general. Distance from start. Okay. Yes, so it's the depth actually, right? Because that's why we have this queue there, because it's the depth in the tree, and those that have the smallest depth, so Fn is the depth, those that have the smallest depth will be done first. So the BFS, which is this one, will have Fn equal to the depth of every node, essentially, right? So basically, it will be choosing those that have this, that are the closest to the start for expansion first. In the implementation, you may actually not need it, because if you implement it right with the queue, it's just gonna work like that, without knowing it. But if you didn't have this queue, if you just had, any, let's say, list, and you wanted to emulate, the breadth first search, you would need to actually pick those from a certain level first. So you would have to first do this argmin of the depth. Okay. So anyway, yeah, it's the distance from start. It's the depth in the tree. Good. Now, how would it be for the UCS, which we just went through a second ago? What would be the node evaluation? What would be you will be taking the minimum of what for expansion? Exactly. It's the cost, the path cost, basically, how you got to every node. Indeed. And how about the depth first search? That's a bit tricky. Can you imagine what? How would you need to set up the fn such that the same formula will apply? Or indeed, yeah. So it's the depth, but in this case, it's sort of the maximum distance from start. So if I just write it like this, it's gonna be the minus depth, because the way the depth first search works, it dives deeper and deeper and deeper until there's nothing to explore, and then it does this backtracking. It goes back a little bit and picks it up there. That's why it's using stack, because whatever comes last will be done first. So basically it goes as deep as it can. That's why you can also implement it using recursion. And after you're done with a certain study, it will backtrack and come back. So indeed, so this is exactly what you need to know. And yeah, these kind of questions, would be also relevant, for example, for the exam, that you really understand what is going on. What the essential differences between the algorithms are. Nice. Okay. So actually, this priority queue could then become a general data structure that you can use for all if you set it up in this way, that you just assign a different fn, which is going to be either depth or path cost or minus depth, and then with a single data structure with a priority queue, you could do all the algorithms. But as we discussed, the stack or the queue are the actually intuitively, conceptually right data structures for DFS and BFS respectively. Okay. Okay, and now we basically moving on to the second part of the lecture. So all of these correspond to the cost from the start, which we will call it backward cost. What we have already traversed in the state space, and it turns out that's not the full story, because it's not the most efficient thing to sort of, in general, that you only count this backward cost, because intuitively, very often you would have some idea. If you imagine you're searching, let's say, in a city or in a maze, yourself, you would probably not do it this way, right? You would probably not just count how many steps you did, but instead you would sort of, because you want to get somewhere, you want to get to the exit, or you want to get to your goal, and you might have some idea where the goal might be. That's what you would try first, and that's the essence of what we will do. What we will do now. So the cost to come, so to speak. And unlike the backward cost, which you know it for sure because you can measure it, and there's no uncertainty with it. For the cost to go, you may have some guess. That's why it's called heuristics. Okay. So it's a function that estimates how close a state is to the goal. So how close you are to the goal in a particular state, but in general for every state. It's designed for a particular problem, and yeah, we will call it HN, so the heuristic value of node n. So we go back to the examples of the cities in Romania, and using So we have cities on the map of Romania, and we have the distances on the road. And we're looking for a heuristics, how far. So, we don't know those road distances. That for that we would have to search. But we're looking for a heuristics that would give us an idea how far it is to the goal from each of those cities. Do you have any idea what such heuristics could be? Right. Yeah, I guess it's hard for you to imagine where I'm getting. Okay, never mind. So let's jump to the conclusion. So a possibility would be a straight line distance. So imagine you don't know anything about the roads, but you have the map, let's say a physical map, and you could know these straight line distances. That the line connecting Arad and Bucharest would be 300, and so this is actually what you see in this map. Okay, no, in this table. So so the straight line distances, like for an airplane, would be this, and this is actually, it turns out this is going to be a useful heuristics, that you get the idea that it's likely that it's going to be closer from Pitești to Bucharest than from Sibiu, because it's closer on the map. But it may not necessarily be always true, because there might be some roads missing, right? So for example, from Craiova to Bucharest, the straight line distance is not going to be, it's 160, but it's going to be quite a lot more, let's say, on the roads. Okay, but we will learn that this kind of heuristics will already help us quite a bit. Now, greedy. So the first example that takes only this heuristic information into account would be, it's called greedy because it's greedy. It's basically looking at the heuristic values for those nodes on the frontier, and it just always takes the minimum. So this is another state space, and so what will happen here? So we will expand S, so that's the start, and get to A. Okay, A will go to the frontier. Okay, now we need to expand A, and we will get B, D, and E. The cost that we had so far, it doesn't matter. Okay, in this case, we're only looking forward, and we're having E with a heuristic of 1, D with a 2, and B with a 6. So we choose 1, and we get to D. Well, we already have D, but that doesn't matter. So the next, but this is removed from the frontier because we expanded it. There's no other, no more paths from here. And so we, on the frontier, we currently have a D and a B. This has 2, this has 6. So we go from 2 and we get to the goal. And yeah, so we're done. But there's one problem, and the problem is that we got there through here, and not through here, because we basically, this was we chose this path because this had an age of 1. So we went through here, and so we ended up on the backward cost, what it actually takes, we ended up with a higher cost than was necessary, because it would have been shorter to go this way. But because we only took into account the age, the heuristic, we didn't get the optimal solution. Age, it seems the age is getting higher, than no point to go there. Right, exactly. So the point here is that the heuristic is only going to be useful if it has some properties, which we will formally look at in a second. So if the heuristic is just wrong, it can have bad consequences. For example, that we actually miss the shortest path because we are misled by the heuristic values. So that's the danger. So if the heuristic is just wrong, then the algorithm using this greedy algorithm will not be optimal. It may not be even complete, okay? Because it will basically, if it's a 3-search version, then it might get stuck. We can also look back here. So imagine you're going from this town, Yassi, to Fagarash. Okay. So you're in Yassi. You can go to Vaslui or Niamt, and you're looking at this table because that's your age and that's your heuristics. So Niamt will have, okay, I don't see it. Okay, 234, and Vaslui will have 199. Okay, so we go to in this case, so Vaslui would have a lower age. Right. So there's something wrong with my example. That's not going to work, that I'm going to be stuck as I want it to be stuck. Or unless, no, because of course, sorry, because my table is wrong, right? Because for my example, Niams to Fagara, from Yassi to Fagarash, but my table only has the values to Bucharest. Okay, so in this case, that's not useful. But you can see it on the map. So Niamt is clearly closer to Fagarash, right, than Vaslui. So I would actually choose Niamt, right? And then if it's the 3-search variant, which is not checking what has been already visited, next I would have Yassi and Niamt on the frontier. No, I would have Vaslui and Niamt on the frontier, but I would add Yassi, which is also closer to Fagarash. And basically I will keep cycling between these two because they would have the lower age than Vaslui, and I will never get out of this, right? In this basic variant, the 3-search variant that is not checking what I have already visited. So because there happens to be no road in this direction, I'm going to be stuck over here. Are we okay? Are we calculating heuristic? So I'll let you. Yeah, well, the thing, yeah, my example was the table here is not really because they are straight line distances to Bucharest, right? So, but I wanted to show something else, how you can go into the dead end, but that's actually not this this table. So that was a little bit confusing. Sorry about that. So I guess you guys are still typing something, but I'll try to move on, but feel free to continue. Heuristic more useful in a more connected graph. Yes, yeah, you're right. So in this particular example, that's it's quite clearly the case. If you're going to have a lot of roads, then this straight line distance approximation is going to be very useful, right? Exactly. But if you have a lot of dead ends like that, it may not be as useful. That's correct. Right. So let's go back to this example. So yeah, so the greedy has this disadvantage that it's only counting the the heuristic, and that's a bit naive, right? Because at least once you're expecting something, but then it turns out different, you should somehow take it into account, and that leads to, so the UCS orders only by backward cost, which we will denote GN, and the greedy only uses HN, which is the goal proximity. And it turns out that the best thing you can do, which this famous A-star algorithm does, is combining these two. So you combine, so you order the nodes by this Fn, which is just a sum of these two. So you have the backward cost, what you have, which is something and then you have the heuristic, which is something that has been given to you. And that's the best you can do under some assumptions on the heuristic, which we will learn about in a second. So if the heuristic is wrong, then it's risky, and you can actually, your algorithm may not be optimal. But if the heuristic is reasonable, which again we will learn to formalize, what does that mean, then it actually is really the best algorithm in town. Okay, so let's look at yet another graph, and we can see how we would run the A-star. So remember, the A-star, the node evaluation on the frontier is this backward cost plus the forward cost. So I'm going to start here, and so maybe we can write out how the algorithm would be running. So the f of s would be the backward cost, it's the start, so that's 0, plus the heuristic. So somebody tells us it's going to cost 3 from here to go, which is 3. So it's 3, okay? So we're going to expand it and remove it from the frontier, and we're going to get to A and to B. So let's just write down a couple of things. So let's see if I manage. So right now we're going to have f of A equal to g of A plus h of A, which is going to be 2, which is, it costs 2, plus this 2, okay, which is 4. Now, how about B? F of B is going to be 2 plus 1. It's going to be 3. So this is lower, 3 is lower than 4. So I'm going to be expanding B and crossing this out from the frontier. I'm not sure I can So we can also write somewhere what the current frontier is. So currently we have A on the frontier and we had B, but we will just delete it and add a G. Okay. And we will now have f of G, which is the backward cost. How did we get to G? We got it there through here, which is 2 plus 3, which is 5. That's the backward cost. Plus a 0, because it's the goal. So it's a 5. Should I stop the algorithm now if I'm in the goal? Let's make a poll. Yes, for that I should stop. Yeah, okay. Yeah, so indeed, I should not stop. It's the same kind of story. And I should still, because I have something on the frontier with a 3. So I should, first check whether there's something coming out from there. Yes, yeah, heuristic value is given for now, exactly. Okay, so I should not stop, but I should pop the this 4 here, which is the A, because B is no longer on the frontier actually. Okay, now I have a problem because I jumped out of the text box. Oh, what do I do?
Create a new one.
No. Okay, so what I should do now is that I should take this, expand the A, and I get to G as well, and that's gonna give me a 4 plus 0, which is a 4, and that's better. And then I can expand that one, which is 4, compared to 5. And then in that case, I'm expanding the goal. The goal doesn't have any, children, but it doesn't matter. But now it's the right time where I can safely stop. So that's what I'm going to do, and I will find the correct path. So similarly to the uniform cost search, the first time you arrive to the goal, you should not stop. Thanks, Philip. G has less distance using A. Indeed, yeah, which is also the case, the backward cost, but it will work out also using the A-star algorithm, taking the heuristics into account. The values of sums. So the node cost is the sum of the backward cost, which is the G, and the forward cost, which is the heuristics. That's the H. So for an A, it's the 2. We got to A from S plus the heuristic, which is this 2. Okay. For the B, it's this 2 plus 1. For the G, the first time we had G, it was this 5. 2 plus 3 is 5 plus 0. But we didn't stop there because we had still this 4, which was lower than 5. We expanded also A, and we got to G as 2 plus 2, which is 4 plus 0. And then only then once after we expanded, we stopped. So the sum, the H is simply the number written here. It's always just this one number, but the G is the backward cost, which can be a sum of, all those edges you had to go through. Is this clear, Elisa? Good. Right. So yeah. So H is a function of the state. it's something, part of the state space, but G is a function of a node in the search tree. So the path matters for G, right? That's what we've been doing, up to now. But for the H, the path doesn't matter. That's all just a property of the node in the state space, not in the search tree. Okay. So another variant. So there are always these two properties of algorithms we're interested in. One is completeness. It means it's gonna find a solution no matter what. And the other is optimality. It's gonna find the best solution. So in this case, the cheapest solution. Do you think that A star is optimal? Is it always gonna find the cheapest solution? Let's make a poll. Vote yes if you think it's optimal. Okay. So it all boils down to the properties of the heuristics. If you have a bad heuristic, it's not going to be optimal, and we will see why. If there are some conditions that the heuristic fulfills, then it's going to be optimal. So let's have a look at through this example. Okay. So let's run the A star here. So we're gonna start from S. So f of S is gonna be G of S plus H of S, which is gonna be backward cost is 0 because I'm in the start. Heuristic is written here, plus 7, which is 7. And let's also write what is on the frontier. So on the frontier, I had basically S, and I'm expanding it now. So I will be removing it again, and I will go to A and to G, right? So that's the expansion. So A and G will be the new frontier. Now, f of A is gonna be backward cost 1 plus heuristic 6, 7. Now for G, it's gonna be the backward cost, which is 5, plus the H in G, which is 0, which gives us which gives us 5. Okay, and so this is now the cheapest on the frontier, 5 compared to 7, which means I'm going to expand goal, which means that's the stopping criterion. So I'm going to finish. Oops, right? So I'm going to finish with a 5 here. But I could have had 1 plus 3, which is 4, right? So in this case, this would not be optimal. So there is a problem, and we will see what the problem is. So moving on, do you see what the where the problem is. Any ideas? Wait, I wasn't following the chat now. Was there some mistake in the calculation I did before? Yeah, it's the bad heuristic. And do you see in where the problem is? Yes. So what exactly is the problem? Exactly. So let's make a poll. What would be the right heuristic for A out of these A, B, C, D? Yes. So you kind of got the idea. Intuitively, it's correct. The correct answer is actually B, but yeah, pay attention to this. This may actually also sort of come up, for example, on the exam. The heuristics, they don't have to be non-negative, okay? It's gonna be, intuitively, in most problems, it's not very meaningful that if they are negative, but the algorithm is gonna work even if they are negative, okay? And, be aware of this. It may actually pop up in the exam. So don't make this assumption if you don't have a reason for this, that they have to be non-negative. But you got the essence right, which is that they shouldn't be pessimistic, the heuristics. That's somehow the keyword. So if the actual cost here is 3, then if my heuristic is that it's less than that or equal, it's fine. That means it would be optimistic. If my guess is it's gonna cost 2, in the end it costs 3, it's fine, because it will not prevent me from exploring that path. Okay. And that's what matters. That guarantees that I'm not gonna miss the optimal path. But this is not the case here, because it's pessimistic. It tells me it's going to cost 6, but in the end, it's going to cost actually only 3. And that's a problem, because I will just not go there, because it tells me it's going to be very expensive. And that's the problem. So that's what the heuristic is, that's not allowed. Okay, because then it's not gonna, it's make the algorithm not find the optimal path. Okay, so this is the problem. Exactly. Yes, that's correct. So it has to be lower or equal to the actual cost, but formally there's no it doesn't have to be bounded by 0. But the from common sense, this is really the important part. It shouldn't be pessimistic. It cannot be pessimistic. Does S also have a bad heuristic? Indeed. Yes, it does. Yes, it also has a bad heuristic. Yes, exactly. It's pessimistic even for both paths. Yes, good question. So the formal term to express this is that the heuristic is admissible if its value is lower or equal to the actual cost, to the goal for every node. Okay, so it's called admissible. And the heuristic is admissible, then A star is optimal. And yeah, so remember maybe in the first lecture I was showing you this video of Shaky, that robot, but that was I think from the 60s from Stanford, and that's essentially where they discovered this algorithm, and until today it's basically the most widely and the best algorithm around, this A star. So it's really an important algorithm. So again, we have this graph search and tree search variant of this. Graph search is the one that has these additional conditions, that you have this explored set that you're checking. So this is the pseudocode. Insert the start node. The set is initially empty of the explored set. You have your frontier. Right, so there's basically, it's still the same thing. The point is that here you have to, the node evaluation is going to be the backward closed plus the heuristic plus the forward cost. So so we could run it on this graph, but let me just check if we have time for this. We might have time for this. But it's going to be basically the same thing. So you might also do it. You might also look at it on your own later. So in the interest of time, let's not go through that. The idea is so for the tree search, there was this admissible condition. For the graph search, there's a slightly different condition. But it's kind of the same idea. The thing here is it's something like the if you this triangular inequality. So if you have a triangle, then the distance, let's say, imagine you have a triangle BCG. The distance here is always cannot be bigger than the sum of the lengths of the two other edges of the triangle, and that's the sort of the essence here. So before we had this, before we had a tree in the space, because we had well, actually, not always, but in some cases we did. In general, for the graph search, there has to be a strong condition, which is that the heuristics is what is called consistent, and admissible we had, that was clear, and consistent is that there is a heuristic value for A and for C. And their difference should be smaller or equal to the true cost from A to C. Okay, so it kind of makes sense, right? It's just a generalization of this, that basically you cannot have any sort of loops on the graph where this would not add up. So you would basically where you would have overestimations accumulating, that the difference of the heuristic values would not match with with the cost that you actually have to spend when you go there. So yeah, it needs a little bit of time to think about this, but basically we would have to go through an example. So I'll see if we do this example next time, but I don't want to take away I don't want to go beyond the time set for this lecture. So HC is 3 if it were consistent. Right. Exactly. So that could that could solve the problem. Yeah. Let's look at this in piece probably next time, because this will take us at least 5 minutes or 10 to really do this properly. So let's keep this one. There was this admissible, which was very clear. The consistent, we have to basically feel free to look at the slides, or we may come back to it next time. So consistent graph search, and all consistent heuristics are also admissible. But it's not easy to invent a heuristics that is admissible but is not consistent. Okay, so these are really sort of weird cases, but they exist. And if you want to sort of get it formally right, and you have to and want to be sure that in all kind of weird cases your algorithm works, then for graph search you need this consistency, and admissibility is not enough, right? But again, these are sort of really special cases. So I think that the time is up, and these are the references. I want you to also, or you have questions at this point?
Yes, I have a question, but I will wait if somebody else has.
I just want to point out something. So you will have an example of this admissibility and consistency calculation of the heuristics in the next lab. So not this week, but the next one. So maybe you don't need to do it in the lecture.
Okay, wonderful, Philip. Okay, thanks for that. So not today, but next week, you're saying?
Yes, it will be the bonus exercise.
Okay, very good. Okay. I think we can take the question.
All right, but it's not a question for this course. Would you mind if we could switch to our native language, because I'm a Czech like you?
Well, okay. So then let me first finish the lecture. Okay. Okay. So if nobody else has a question, so I wanted to homework. We can use the straight line distance as the heuristic. That depends on on the assignment or on the problem. It has to be something given to you, or you have a specific homework in mind. Maybe Philip can answer that question.
He's talking about the first assignment, I guess, the one where they have to implement A star.
Yeah. And
well, the deciding on the heuristics is something that I think is included in the problem. Like you have to think about it and decide it yourself.
I see. Okay, so we don't want to. I see. Yes. And give away the solution. Okay, one thing I want to mention before we finish is the following. Let me share my screen. So we're here, and we did this lecture today, number 3. I will upload, so these are still slides from last year. I will upload the slides from today, also slides with notes where you actually see how the things we did online, how they are computed. It's going to be on the slide version with notes, and you also have the recording. By the way, there is also this YouTube channel that Tomáš set up, and the recordings are also available in the Brute. But for next week, let's do the following. So there is the courses from Berkeley, from University of California, Berkeley, that are there is some overlap with the topics, and they are given by Dan Klein and Peter Abil, and they are, I think, very well done. So let's do an experiment. So for next week, I ask you to watch this adversarial search beforehand. Okay, so please watch this lecture. I think it's 1 hour. I have more features. And we will have our lecture at 10. I will expect that you have watched this, such that basically we can, either go faster or make a shorter lecture. So, I don't want to reinvent the wheel to just, replicate the content that is well done here. So please watch this video. You have linked it from here prior to the lecture. And we can then basically go faster and also make it more interactive. So I will assume that you have watched that video, and you can already come up with questions. And so we can basically use the time of the lecture to make it more interactive. Okay, so please watch this before the lecture. Any questions or comments today? And I will stop the recording.